In this video, we will take a closer look at how NMR works and use that to understand exactly why for certain NMR signals we see more than just a single signal, but rather a very complex splitting pattern. The reason that splitting occurs is that because nuclei themselves are also magnets, that means that each nucleus in a molecule is going to feel the external magnetic field of the NMR instrument, the induced secondary magnetic fields of the electrons, and finally, the magnetic fields of all the nearby nuclei. So the interaction between the neighboring nuclei magnetic fields and the nucleus whose signal we are looking at is called a coupling interaction. This coupling is also called more specifically J-coupling. It's considered a spin-spin interaction, so it's nuclear spin interaction, and it's taking place kind of through the bonds of the molecule. So not through space, it has to kind of travel through the bonds. So I think it's worth taking the time to understand why coupling leads to changes in signals in NMR. All right, so we'll consider a system which has two nuclei, so we'll say proton A and proton X here, nucleus A, nucleus X. And if you have these two nuclei and just kind of assume there's nothing else in the rest of the molecule, then we would have the possibility of having our nucleus A being spin up, and with that, nucleus X could be either spin up or spin down, so two combinations. And then if nucleus A were spin down, then nucleus X could also be spin up or spin down. That overall leads to kind of these four combinations here. For convention, people who study NMR or deal with spins as their work will label these as being an alpha spin or a beta spin, where the convention is that the alpha spin is lower in energy. The more important thing for us is that if that happens, that you have these two nuclei that are coupled together, then they will start to kind of differentiate energy levels. So actually for two nuclei that are coupled together, there are four possible energy levels. Spins kind of both alpha, alpha beta, beta alpha, beta beta. This is a situation that we can think about where there's actually no coupling or splitting in the NMR. So there are four different energy levels, but there is no coupling in this situation. This applies to a case where the two nuclei, the two protons here in this molecule, are symmetrically equivalent. So they are chemically in the same environment and they are magnetically equivalent. So another piece of physical chemistry that we'll just have to kind of understand to be true is that with all of these energy levels, it's not the case that you can just jump between any of these energy levels at will. There are what are called forbidden and allowed transitions based on what are called selection rules. And at least in the context of NMR, we can only flip one spin at a time. Those are the only possible transitions between systems. We can't do a transition where both spins flip. Because of that, there's really only four possibilities that I'll outline here. So in orange and purple. And it turns out that if the two nuclei are totally identical to each other, then the spin flipping can only have two different energies. So if you kind of look at what's going on here, so we'll start with the top left. What I'm getting is I'm flipping the alpha blue to a beta blue spin. That is associated with a frequency for kind of the nucleus or proton A here. And at the bottom right, I have that same process. I'm flipping the spin of the proton A. That means the blue alpha is going into blue beta. These two energies will be exactly the same. So I'm giving this as a frequency term here, but these will be identical. So that means that it doesn't really matter if we're thinking about this situation or that one being excited to a higher energy level. They're both going to have the exact same energy of excitation. So they will both show up at the exact same location in the NMR spectrum. The same thing is true for flipping the red nucleus or the red proton. Again, there are two possibilities because we can go from alpha alpha to alpha beta or beta alpha to beta beta, but those are the exact same delta E, meaning they have the exact same frequency here. So in the data, that shows up like this. We have a signal for the proton A single signal. This encompasses both of these possible transitions. And then we have a separate signal somewhere else. So here I'm showing it more upfield for proton X. Again, a single signal corresponding to two energy transitions that are degenerate to each other. So again, the reason that identical nuclei show up as a single signal at the exact same location is because all of the possible transition involving that nucleus doing a spin flip have the exact same delta E. So now let's look at a situation where nucleus A and X do couple together, and so that is called AX coupling. So what happens there is that, so I'm going to have my new energy levels here, and I'm going to kind of overlay them on the original. What happens is that the two of the energy levels are increased, so the alpha alpha and beta beta are increased. That's because those spins are coupled, and so having them aligned together, it turns out to increase energy a little bit. And then the other two energy levels are decreased in energy because now they're opposed spins. So this is just something that happens and we'll kind of accept. So let me drag that over here. What that does is that it changes the delta E's between the four energy levels in a way that now all four are different. So I still have the exact same identity of my two spins, but the differences in energy and thus the transition energies are different. So we can start at the top left again. So what we see mathematically is that we have an energy gap here that is equivalent to this original frequency that we had in the no coupling situation, plus a term that we call plus j over 2. The bottom right here now is the same conceptually, except that now instead of adding that extra energy, we are subtracting it because this gap has decreased. Same thing for the frequencies of proton X here. In the top case, we increase by a factor of j over 2 as a constant, and then on the bottom left, we decrease by a factor of j over 2. The point being that we have now four different energies of transitions, which means that we should expect for these two hydrogens a total of four different signals in the NMR. And that is exactly what we see. So the data would look something like this here, where we have at the same kind of overall location as we did with no coupling. So here we had a single line. Now instead of a single line, we have two possibilities. One, which is red, which is slightly higher in energy. So I'm showing that as the red line here. And then one which is orange, which is slightly lower in energy, which I'm showing as the orange line here. Same thing for the signal for nucleus X. That gets split into two new signals, one corresponding to the higher energy case, one corresponding to the lower energy case. And so if you look back at the math here, what you can see is that we added j over 2 to some of the energies. We subtracted j over 2 from the other energies. So in total, that means the difference between those two signals is going to be just j. And that is where this term j coupling comes from. And so we call the spacing here, the frequency spacing, to be the j value. And the j value is always given in units of hertz. So one last thing I want to point out here is that what we've done is we've taken a single line and split it into two lines. And so the terminology for this is that we've created a doublet for the signal of proton A. The same is obviously true for the signal of proton X. That's also gone from one line into two, so another doublet. So the magnitude of the j value will change the spacing of that splitting. And so we want to try to be able to understand what the impacts of structure are on the magnitude of j value, because that can help us to interpret an NMR spectrum. So there's two factors that we think about. The first being that the number of bonds between the nuclei will change or at least affect the j value. That's often given in a terminology like this, where the number is written before the j. So you could have a 1j or a 2j, etc. coupling. This should make a little bit of sense because coupling is supposed to be a through bond interaction. So if we're going through bonds, then the number of bonds should matter. The second thing that matters is that the geometry, so kind of the angles that the bonds are to each other, and also the nature, so sigma or pi, of the bonds makes a difference. And we'll look at each of these as we go through different j values. I think it's useful to think about j values just going in numbers. So we'll start from the smallest and work our way up here. So 1j coupling values are very large because the two atoms or the two nuclei that are coupling are very close to each other, so the effects are greater. The place this shows up in organic molecules most of the time is between carbon and hydrogen, because all of our molecules have carbon-hydrogen bonds, right? And those are one bond long. So this is carbon 13 coupling to proton. This will come in at about 100 to 300 hertz, so that for a J value is an extremely large number. However, we don't actually in data usually see any 1JCH showing up. This is because in the proton NMR we don't see it from the perspective of the hydrogen, because only 1% of the carbons are carbon 13. So the vast majority of our data is coming from protons that are bonded to carbon 12s, and so there's no coupling there. The 1% that does have coupling, well, you do see that data, but it's very small with respect to the rest of the data. From the perspective of carbon, so in carbon 13 NMR, what happens is actually the experiment that people usually run just by default decouples the carbon and hydrogen from each other. So there's all sorts of complexity when it comes to NMR experiments, but you can actually turn off this coupling or hide it in the data, so we just don't see it because the vast majority of carbon 13 NMR has it decoupled. So we'll move on to 2J coupling. So we'll focus on proton-proton coupling, but none of these concepts are exclusive to proton-proton coupling. The J values change depending on the identity of the elements that you're looking at, but conceptually the ideas are still similar. So for 2JHH, this is called a geminal coupling, where geminal refers to twin because the two hydrogens must be attached to the same carbon for this to be the case, for there to be two bonds apart. And the pattern is that the geminal coupling constant will depend on the hybridization of the carbon atom. So for an sp3 carbon, the 2J value is between 2 to 15 hertz, and generally speaking it's going to be about 12 hertz. So there is a wide range, but 12 hertz is the most common value. If we go to the sp2 carbon situation, I think of this as the angle between the carbon-hydrogen bonds here changes a little bit. So then that changes some of the physical factors behind all of the coupling constants. And so for an sp2 geminal carbon, its hydrogens have a coupling constant of only 0 to 3 hertz. So next let's look at 3J coupling. This is called vicinal coupling, where vicinal refers to neighbor, because the two hydrogens here, the two protons, must be attached to neighboring carbon atoms. This is the most relevant type of coupling that's observed in organic molecules, because if you think about the way organic molecules are, there's a lot of carbons attached to carbons who each have their own hydrogens on them. So we'll start off looking at the sp2 carbons this time. So something that happens now with alkenes is that you have different possibilities in terms of geometry. So we can have the cis protons here. When they're cis, you get a coupling constant about 7 to 12 hertz. When the two protons are trans across the double bond, then the coupling constant increases a lot. So this is now 13 to 18 hertz. So if you're dealing with alkenes, this is a nice tool to try to distinguish whether an alkene is cis or trans. Looking at the sp3 carbons, the coupling constant here can range a lot, so we have a wide range of 2 to 20 hertz, but the vast majority of the time we see a 7 hertz value. So in normal cases for an sp3CH and an sp3CH coupling, we see coupling constants about 7. The reason there is such a wide range is because there is a dependency of the coupling constant on the dihedral angle between CH bonds. So what the dihedral angle is whenever you have a 4-atom system, you can talk about the angle from a Newman perspective between this bond, CH bond, and this CH bond. So in the Newman projection, that would be the bond coming from the atom in the front here versus the bond coming from the atom in the back, where that's your dihedral angle. There's all sorts of vector math behind this, but basically the vectors of these directions affect the J value. This is reflected in what's called the Karplus relationship. or Karplus equation. We're not going to look at the actual equation, but just look at the outcome of the equation. And so what we see is that there's a dependency of the J value on the y-axis on the dihedral angle here on the x-axis. So let's go over the most important points on this plot to try to remember. So when the two atoms in question, the two nuclei in question, are staggered and anti to each other, so the dihedral angle is 180 degrees, that puts us way up here on the Karplus equation. And what you see there is that this is when the J value is going to be the largest. So on this equation, that comes in at 15. So again, antiprotons are going to have very large J values. And that's exactly actually what you see up here when it comes to the alkene. These two CH bonds are anti to each other. That's why the J value here is high. We can take now the Newman projection where we've kind of rotated our dihedral angle to be orthogonal at 90 degrees. When that happens, I think of this as the vectors are now orthogonal, so they don't really contribute to each other very much. So our dihedral angle is 90. Our J values are very low, so close to 0. As we go back up again, now to being totally eclipsed, where the dihedral angle is 0 degrees, again our vectors are kind of aligned and then thus can communicate with each other a little bit. We get back to a larger J value. On the Karplus plot here, that's at 13 Hertz, so maybe a little bit smaller than the anti version, but still a large J value. So going back to this range of J values here for the sp3CH situation. So the reason we usually see a 7 Hertz J value for normal kind of alkane protons coupling is because what we're really seeing is the average of all conformations. The Newman projection of whatever molecule we're looking at, so the Newman projection of this bond is going to be rotating around to some extent and thus averaging between all of these different values, or really I guess all of the values here. And so depending on the conformation, there's going to be a different coupling constant. And on the time scale of the NMR instrument, it can't tell necessarily which conformation we're in, so it just sees kind of the blur of all these averages. That turns out to be around here at 7. What that means is that in certain molecules, of course, conformation is slow, so then those molecules will have more distinct 3J coupling values. So a case for that would be in, for example, cyclohexanes. So cyclohexanes, if you look at the blue protons here, these blue protons are both axial, and if two groups are axial and adjacent on a cyclohexane, they are anti to each other, and so the coupling between these two protons is very large, more on the order of 15 Hertz rather than 7. If you look at the coupling between, for example, one of the red protons and one of the blue protons over here, the vicinal coupling, that's very small because we're close to being orthogonal. And the same is actually relatively true for the two red protons here coupling. Again, our J value will be a little bit smaller than 7. Finally, you have the geminal, so the 2J coupling between red and blue here, and of course that should be very large because this is an sp3 carbon with geminal hydrogens. So the 3J coupling can be a very useful tool for cyclohexanes and other rings to figure out what is diaxial to each other or anti-diaxial to each other, and what is kind of equatorial to each other, etc. So beyond 3J couplings, there are 4J and 5J couplings that are accessible to protons, but these are definitely not as common because our distances between the nuclei are starting to be too big for the effects of one nuclei to be felt by the other. So usually what we see is that this coupling, so we'll call that long-range coupling, is only observed when there's pi bonds between, kind of along the path between the two nuclei. In general, these 4J and 5J values will be very small, 0 to 3 Hertz, and really typically they're going to be just 0 Hertz. So in other words, we just don't see any coupling at all. Those energy levels aren't affected. So there are situations, of course, where we do see them. That's why we need to talk about them. One of these is on aromatic rings. And so this is a 1, 2, 3, 4J coupling between protons. This is the meta relationship in an aromatic ring. So if these two hydrogens were not equivalent, with respect to the rest of the molecule, then we would see a coupling constant of 1 to 3 Hertz. As drawn, they are equivalent, so we'd see no coupling because those delta E's were the same. But I should make this I should put something here to make them not equivalent so that we do see a coupling. If we look at the 5-bond coupling now, so 1, 2, 3, 4, 5, that's very small. So usually it's between 0 to 1 Hertz, so often not observable. If it works for an aromatic ring, the same type of coupling ought to exist for just regular alkenes, and that same type of coupling does. So we can look at the 4J coupling between protons like so. So this is between protons that are protons on. So this coupling is between protons on groups that are trans across the double bond here. That comes in at this relatively low J coupling value, so between 0.5 and 2.5 Hertz. Usually observable, and that's because in part due to the trans nature increasing J values. That's in contrast to when we're looking at the cis groups here. When these are cis, then the J value is a little bit lower, so more like 0 to 1. Finally, we can also see this in triple bonds. So the alkyne CH can couple 4 bonds away to another hydrogen, and this is actually relatively stronger at a 2 to 4 Hertz range. Part of an explanation for this would be that we have a shorter CH bond and a shorter CC bond here that may overall contribute to these protons kind of being closer together, so their nuclei communicating just a little bit more effectively. So splitting doesn't end there because each nuclei in the molecule doesn't necessarily have to be next to just one other nucleus that it's interacting with. When you have more nuclei around, more complex splitting patterns or multiplicity will emerge. So we'll focus on first order splitting, and that's the case where the difference in chemical shift between the two nuclei is large compared to the J value. So that was the case in the energy level diagram that I showed you at the very start of this video. There's a few rules. So one is that in first order splitting, if nucleus A is coupling to nucleus X, then nucleus X is also coupling to nucleus A with the exact same amount of J value. Coupling is mutual. This should make sense because if we're thinking about a delta E, it doesn't really matter if we're going up or down, that's the same J value. So let's go through some scenarios. If all of the coupling to our nucleus that we're considering are equal, so if our nucleus has a bunch of other neighboring nuclei, but all the J values there are exactly the same, what we'll see is there are 2 times the number of neighbors times the spin of those neighbors plus 1 total different lines in the signal. For us, we are focusing on hydrogen. So for proton, spin is just 1/2. Really, that means that for our hydrogen, if we have n neighboring hydrogens that we're considering as coupling, then we will see n plus 1 lines. That shows up in a really nice pattern, so I will pull up the patterns here first and I'm going to show you the scenario. So we'll start off here on the very left. So when we have our prospective proton here, and let's say it has 2 other neighboring protons that we care about coupling with, then for the blue proton, the signal should have 2 plus 1, or 3 total lines. That's what we see here, 3 total lines. That's a triplet. If we have now our blue hydrogen with 3 neighboring red hydrogens, then we have 3 plus 1, or 4 total lines. That's called a quartet. So on the very right here, we have a fairly large amount of splitting. So we have a blue proton coupling with a total of 8 other red protons, all of which apparently have the exact same J value in terms of coupling with our proton. That shows up as a non-net, or 9 total lines with n equals 8. And so if you're looking at the data for the non-net, you see that the outermost lines are very, very small, so not very intense at all. The vast majority of the intensity is in the middle. And so this reflects that these outer lines are indicating a situation where all of the spins are, let's say, alpha, or all of the spins are beta, right? And those are very unlikely from a probability standpoint, so their intensity is very low. If you're looking at these patterns, they're nice and symmetric. This reflects Pascal's triangle. The way this works is you can actually kind of use this to figure out the pattern that will emerge. So for a signal that has no coupling, n equals 0, you just have a single line. If n equals 1, you do couple, so you kind of split that 1 down in this triangle. You get 1 and 1. As you keep going down further rows, what you do is you do 1. It doesn't add to anything, so you just get 1 here. The middle number 2 comes from 1 plus 1, gets you to 2, and the right is just 1. And as you keep going down, this is a ratio of intensities, so if you have 1 and 2 right here, that gets you to 3 and 3 in the middle. That's what you see for the quartet. So the ratio of intensities is 1 to 3 to 3 to 1. Again, this all comes from probability. This is just a shorthand way to figure out those intensities. In the end, what really happens with people is they kind of just remember these patterns. So that was when all the couplings are exactly the same. Now let's look at what happens when you have multiple different coupling values to your proton. And in that situation, there's two possibilities. One is that for our hydrogen, or our proton, all of its J values to neighbors are different. If that's the case, you will see 2 to the n total lines in the multiplet signal. So let's look at some examples of all the 2 to the n lines. So let's focus first on the simplest one here. So a total of 4 lines. What's happening there is that for the blue hydrogen, that's our perspective, we have a J value to the cis proton. So that has 1 J value, and we talked about how that's different from the J value to the trans proton. So J2 here is what I'm calling it, is different from the orange J1. Right? So those two J values are not equal, which means we should expect for the blue hydrogen 2 to the n, or 2 to the 2 signals for the 3 protons that I'm showing here. That is exactly as drawn here. The trans J value is the bigger one, and the cis J value was the smaller one. And so in the data, that corresponds to that distance, and maybe a little hard to see there, but the smaller J value corresponds to that distance. So in your mind, you're kind of seeing that first I take a signal and I split it into a large doublet, and then I split it again into another doublet, but not as much. And that's this 4-line pattern that shows up right here. And we would expect these 4 lines to be equal intensity because doublets are always splitting from one signal to 2 smaller signals of the same intensity. Because of the way that this splitting is happening, we call this pattern a doublet of doublets, so abbreviated DD. And so what's being shown to the right here are then just more complex situations of doublet of doublets, etc. At the very right, we have 5 Ds there, so that's a doublet of doublets of doublets of doublets of doublets. So that means this is a signal for a hydrogen that has 5 neighboring hydrogen nuclei that are all coupling with a different J value. That's probably a less common occurrence when it comes to our molecules. A more common occurrence is that some of the J values are the same and some of them are different. If that's the case, then you get kind of mixtures of different splitting patterns. So let me pull up some examples here. So here what we kind of can see is that there's some features of doublets showing up in this pattern, and then if you look at the bigger picture, it looks like a triplet, right? And that's indeed what is happening. So this would be a triplet of doublets because we have a large J value for the triplet. That's kind of from the signal perspective, I'm doing this. And then we have each of those signals then split into a doublet, like so, but preserving kind of the initial intensity of the triplet. So this convention is always the case. We always kind of name these from largest J value to smallest J value, which means that on the very right here, you notice that this has also got kind of a doublet appearance and a triplet appearance, but the doublet coupling is bigger looking, so then we call this a doublet of triplets, or a DT, where those are our respective J values. And then in the middle, we have a quartet of triplets, which you can kind of see the 1 to 3 to 3 to 1 intensity pattern for the triplets. Just in case here, our J values are reflecting those couplings there. So that was a lot of information about splitting, a lot of complex patterns that can emerge out of splitting. I'm going to go through 2 examples here of how we can use splitting to help us kind of match data to our molecules. So we'll start off just by being given a molecule and try to predict its splitting pattern. So definitely the first thing we want to do is just to make sure we understand where all the different hydrogens are. So if I fill these in here, looks like we have 4 different types of hydrogens, so we'd expect 4 different signals overall. And then the next thing we want to do is to look for 3J or vicinal couplings that might be happening. And if I look at this, and I look at the gray protons here, 1, 2, 3, this is an oxygen, not a hydrogen, so no coupling. 1, 2, 3, no hydrogens to couple with. So that tells me that these 3 hydrogens have no 3J couplings. These 3 hydrogens are also identical to each other, so I don't need to worry about them coupling to themselves. So I expect the signal for these 3 hydrogens to show up as just a singlet, right? So just a singlet, or S. If I look at the top right there in purple, those 3 hydrogens, those are in the same situation where there's no 3J couplings or 4J couplings, so another singlet. Now, if I look at the orange hydrogen, the orange hydrogen has 3 neighboring nuclei that are 3 bonds away, right? So 1, 2, 3. So then my next question should be, are those J values going to be all the same? And the answer is yes, because if I am taking the perspective of this hydrogen, I look at these 3 red hydrogens and I see that these 3 red hydrogens are all equivalent to each other. So in the end, they're going to all couple the same to the orange hydrogen. So then, because that's a all J values equal situation, I can do the n+1 rule. So 3 neighbors plus 1, that gives me 4, which tells me that's a quartet that I expect. From the perspective of the red hydrogens, each red hydrogen is coupling to the orange hydrogen, so it has 1 neighbor, and we ignore the other red hydrogens because they're equivalent to the red hydrogen. So then with 1 neighbor, we expect to see a doublet, right? So in interpreting the NMR and going to actual data, I would expect to see singlet, singlet, quartet, and doublet. As a further step, I should figure out my chemical shifts. So in this molecule, I should notice that I have the gray hydrogens and the purple hydrogens being, relatively speaking, in similar positions near carbonyls. So I would expect these to show up in similar chemical shifts. And I would expect that to be around 2 parts per million in proton NMR. If I look at the orange hydrogen, that's on a carbon that's directly attached to an oxygen, in addition to being close to the magnetic anisotropy of this pi bond here. So I'm going to guess that this one is going to be closer to 4 parts per million in chemical shift. Finally, I have these 3 hydrogens, which are a little bit removed from this oxygen right here. So I'm going to guess that this is closer to kind of the 1.5-ish. So here's the actual data for the molecule. It's often easiest to start your way from the downfield side of the spectrum and work your way upfield. So if I look here, I do have a nice quartet. So that would be right away what I would assign to the orange proton. Kind of moving further down here, it looks like I have a doublet here at 2.1 ppm. And if I go a little bit further, then I have another doublet at 1.4-ish ppm. And so that should strike you as strange. That doesn't make any sense at all. Why do I have 2 doublets when I didn't predict that? So something we have to be careful of is that 2 singlets next to each other, very close to each other, looks exactly the same as a doublet. So what I'm looking at here is actually 2 singlets right next to each other in a way that looks like a doublet. So I have the one line there from the purple, and the second line there from the black or gray hydrogens. They just happen to be next to each other in a way that makes sense for a doublet. Right? Looks like a doublet, is not a doublet. The last most upfield signal is going to be from the methyl group in red, right here. And so that would be an assignment of this NMR spectrum. And we can see that, my guess of chemical shift for the quartet actually was a little bit too conservative. I could have shifted even more. So I should have taken into account the fact that I have the shift of just being next to the oxygen in addition to more of a shift from being next to the magnetic anisotropy. A final comment about the spectrum is you notice there's a signal here at 0. So that's the reference signal. There's several different types of references we use in NMR spectroscopy. So one of them is just the solvent that's used for the sample. And then the other is an additive, which shows up at 0, and that is called TMS. TMS standing for tetramethylsilane. And what that is a silicon with 4 methyl groups bonded to it. Turns out that's a convenient standard to use as our reference of 0. So that's often added to NMR samples to help calibrate the rest of the signals. Let's look at this molecule here. So again, I go through, figure out what my different hydrogens are, try to figure out different J values. So for the gray hydrogens, I would expect to see the doublet from the red hydrogen and then a different doublet from the orange hydrogen. So I definitely would expect to see a doublet of doublets. For the red hydrogen, then, I would see a quartet here, because I have the 3 gray hydrogens, and then I would see a doublet from the orange side. And then I want to take into account the fact that the trans coupling across the double bond should be bigger than the kind of vicinal looking coupling here. So for the red hydrogen, I would expect to see then a doublet of quartets, because I'm listing the doublet of the bigger J value first. And then likewise for the orange proton, I should have a large J value here, and then a smaller J value to the quartet. So again, I would expect a doublet of quartets. And so I'm just going to show you the doublets of quartets here. And what you see is that they actually look fairly different. And that's because it depends on whether the methyl group here is cis to the proton of interest or kind of geminal looking to the proton of interest, right? So this is a long range coupling here now. And so we would expect that the orange to gray should be much smaller of a coupling. That's a 4J coupling compared to going from red to gray, which is a 3J coupling. And so based on that, then I would assign this to be the red hydrogen signal and this one to be the orange hydrogen signal. That was a lot of information about splitting in NMR spectroscopy. Hopefully what we can take away from this video is the ability to take a given molecule and predict what its splitting patterns and signals will look like. And the next step would be able to take a spectrum and use its splitting pattern to help refine the actual structure of a molecule.